All right, hello everyone. So this is going to be our final lecture, the lecture for 416. As far as new material is concerned anyway, I intend to save the last two lectures, for review, and then our final, as we can see from the syllabus, will be the following Thursday. Okay, so uh, as I have mentioned before, we have assumptions for our linear regression. And as with everything else, depending on if and how severely the assumptions are violated, it can kind of render some of the analyses that we might want to perform, such as confidence intervals, or even testing whether um, the relationship between the variables is statistically significant, things like that. If the assumptions are violated, then it can render those things really not accurate. Okay, so it is important to make sure that the model appears to fit properly, okay, or that the assumptions are satisfied. And so to recall, we have four assumptions. All of the assumptions are about the random error terms here, the epsilons. Okay, and it doesn't matter whether we have a multiple linear regression model like this or simply the simple linear regression model, okay, right, which is just a special case, right, just the simplest version. Doesn't matter, the assumptions are all the same, and that those are that the random error terms all have expected value 0, okay, that the variance is the same for all of the error terms, that they are independent, and that they are normally distributed, okay. And that can basically be summarized, let's see, well, it was in the homework 5. It can be summarized that the epsilons are independent and identically distributed normal distributions with zero mean and the same variance. Okay? And so uh, there's really two plots that we're going to need to look at in order to verify these four assumptions. Okay? The first is the first graph is only used for the normality. Okay, we assume that these epsilons are normally distributed. Okay, so just simply think about how we would normally verify normality for just like a data set. We would do that QQ plot, that QQ norm. Okay, and right, we want a nice 45-degree line, and then that indicates that the data appears normally distributed. Okay, so these random error terms, these epsilons, these are not observed. Okay, however, the residuals are kind of a proxy for the error terms. Okay, so the residual again being kind of how far away our model predictions are from the observed values, right? Y is the observed value, Y hat is the fitted value, or the predicted value for that Y based on our model. So Y minus Y hat, the residuals. What we can do is we can see if these are normally distributed, right? For each observation, we can take what we observed for that observation minus what our model predicts for that observation, right? For that observation, plug its x's in, right, into our model, plug all of its x's in, and it'll spit out a y for us, a y hat. And so we can do that for each observation, and then we will have a set, right, from I equal 1 to n, our sample size, we'll have a set of residuals. And so we can see if that set of residuals appears normally distributed. And if so, that is the best way to indicate whether we have evidence that the error terms are normally distributed. Okay? So as I said, it's just the QQ plot, right? We're going to have like our standard normal quantiles here and our residuals here, and we would like a nice 45-degree line. And if so, that indicates that they're normally distributed. Again, just to refresh on the QQ, right, this all looks good. We would like them to be close to the line, but also on both sides of the line, right? We don't want them all. So all of this is great. And then we see kind of starting right here, the points are all on this side of the line and they kind of even go up. So we kind of miss it a little bit right here, right? But it's not horrible. Okay, it's not horrible, but clearly this upper tail is not as good maybe as we would like it. But if this was my data set, I would say that the residuals are roughly normally distributed based on this plot. Okay, this would not cause me to have major concern with the model. Okay, and of course down here is perfectly fine. Okay, so that is the normality, but we still need to talk about them having expected value, constant variance, and independence. Okay, and there's something called a residual plot. Okay, this is basically to check everything else, and not only does it check for these, okay, um, okay, it also can indicate sometimes where the model is inadequate, and I'll show you a nice example of that in a minute. Okay, but so it can indicate whether the expected value is 0, whether we have constant variance, and whether they're independent. Okay, so whether there's correlation. If so, right, then they're not independent if they're correlated. Okay, so if everything holds, then the residuals, right, y minus y hat, and the fitted values, y hat, should be independent. Okay, and that's something that can be shown. And if the residuals and fitted values are independent, right, that means that knowledge of one does not impact knowledge of the other pretty much. And so if we were to plot the residuals on one axis and the fitted values on the other axis, if the two quantities are independent, then what we should see is no pattern whatsoever, right? Because if they're independent, then it should just be a random cloud of points, a random scattering of points if they're independent, right? If one was related to another, that's when we would expect to see a pattern of some sort. Okay, so when we look at this residual plot, that's what we're going to be looking at. And we would like a nice random scattering of points. Okay, so here we go. We can see we have residuals versus fitted values. And again, this is what the residual plot is going to be. And what you can see here is basically a random scattering of points. That's what we want. Okay, that indicates that our assumptions are satisfied. Notice this dotted line at 0. Okay, that is, right, one of our assumptions is that the expected value of the error terms is 0. So what we would like is we would like these residuals to be randomly scattered about 0, right? We would like basically half to be below and half to be above, but also in a random way, right? Not, for example, if we had all of these were low and all of these were above the line, right? That would be a bad thing, okay? But what we want is for each point on the x-axis, we want the residuals here to be scattered about 0, okay? And we don't want some nice clear pattern, okay? And we want the scattering, how far they are scattered, to be consistent, okay? And I'll show you a nice example of what I mean by that. Okay. But this is a great example of a residual plot where all of the assumptions seem satisfied. Okay, so here's an example. Here's our regression line going through our data. Okay, but here is our residual plot. This is an example of a bad residual plot. Okay, Not because of this, okay? The first thing your eye might be drawn to is this kind of outlying observation here. This is actually not um, an assumption violating thing here, okay? This just happens to be that one of the observations has a very large predicted value, okay? That actually has absolutely nothing to do with whether the assumptions are violated or not. This is not a bad thing, okay? Just happens that one observation in the data set is kind of a lot bigger than the other ones. What is bad is if you can see right here, let's look at low values, low fitted values. Okay, so basically low predicted values of y. Look at how far they're spread on the y-axis here. Okay, they're very spread together, right? Nice and tight. The residuals are very small. But what happens as we increase the fitted values, right? As we increase the fitted values, what happens to the spread of these residuals? Well, they're really tight here. Go over, well, they get a little bit wider, get a little bit wider, get a little bit wider. Okay, this is commonly what's called the megaphone shape. You could almost draw a line right here and right here, right? Almost like a greater than sign, right? Or a less than sign, whatever you want to think about it. Okay, and that indicates that for low fitted values, right, think about this as the spread on the y-axis, how much variability there is in the residuals is very little. But as we get bigger and bigger fitted values, the residuals are taking a wider range of values, okay? And that's a bad thing. This indicates that the variability, the constant error variance, which recall is that complicated term heteroscedasticity, but it indicates that we have non-constant error variance because, for example, if we take a point here, like a fitted value of 1, think about the variance here is very small compared to the variance, say here, which is very large, right? There's these residuals cover a much wider range of numbers than these residuals, meaning the variance here is much smaller than the variance here. And again, that is one of our assumptions that the variance is the same. Okay, the fact that there's this big spread here would not be a problem as long as this spread here was also just as wide here and here. Okay, so again, a wide spread is not an error, a violation of the assumption, provided that that wide spread is the same, right, for all x points. Okay, but if we have a real narrow here and real wide here, then that's non-constant error variance. And this is one of the most common things that you see is what we refer to as this megaphone shape. Okay, and sometimes you could see it in the reverse direction, but it's much more common to see something like this, where for basically low predicted values of y, there's a lower spread, and as we predict larger and larger values of y, there's more variability in those predictions. Okay, that's the most common thing to see. Okay, pretty much with all of the assumptions, there are tricks to try to correct them. Okay, so when you say you've got a model like this, right? It looks like, in this case, it's well, right, we can graph it, so we're looking at a simple linear regression model. Sometimes you want to try to modify, you don't want to just like scrap everything and say, well, right, just from here you can kind of clearly see that this model looks like it fits the scatter plot well, like it could be an appropriate model. But so you don't want to just scrap it whenever one of these residual or one of the assumptions is violated, right? What you would like to do is to try to correct this violation in some way so that you can keep your model, right? You don't want to just throw your model away because one of the assumptions is violated. And we'll briefly talk about some of the ways, but we're really not going to go in depth into trying to correct when an assumption is violated, for this course, I mostly really just want you to understand what the assumptions are, and using the two plots, the residual plot and the QQ plot, how you can check whether the assumption is satisfied or not. Okay, so in a case like this, there's a couple things you can do. Okay, one of the common things that you can do is to try to transform the response variable. Now this is kind of annoying because as it says here, common transformations are to take the log of y or the square root of y, and sometimes doing this corrects this issue. But I want to mention that it's kind of annoying because let's just say you transform and you're modeling the natural log of y. Okay, so what does that mean? Well, what that means is normally your model is this, right? Y is equal to beta naught plus beta 1x. So, right, for every one unit change in x, y changes by beta 1, that type of thing. So if you instead model the natural log of y, just think about putting natural log of y here, then we have natural log of y is equal to beta naught plus beta 1x. So again, now trying to interpret the slope for every 1 unit change in x, the natural log of y changes by beta 1, right? So thinking about that in real life terms, the natural log of y changing by 1, I'm not sure that that's going to necessarily have a nice interpretation for anybody, right? If you just tell them that. Okay, so it kind of hurts the interpretability because I can't think of a concept where we would just naturally talk about, okay, I'm going to change this by 1 and I'm going to change the log or the square root of this by something else. So it hurts the interpretation. However, sometimes that could be necessary in a case like this, okay? If you transform that, sometimes you could transform this, okay, and fix this. And so to do that, here's an example here, right? Normally we have Lm y tilde x, and it looks like peak demand is y. So it looks like here we're doing the square root transformation, and so you can see he's putting square root y tilde x. And if I wanted to do natural log, right, then I would just put log y tilde x, okay? And something that it mentioned up here, that's one of the most common things, but there's a more complicated but also very common way to try to fix this is called weighted least squares. Okay, well, we're really not going to talk at all about that. So let's see if there's a new plot or not. So now we've got the square root of y tilde x, and we're trying to see if that might fix this non-constant error variance. Okay, I'm not going to expect you to try to fix these, but I just want to see if there's another graph. Okay, so now you can see we have square root, right? This is on the square root scale. Again, annoying, but we've still got this nice relationship. And now looking at the residual plot, it looks a lot better. Okay, here's our remember that one outlying observation. Again, that has nothing to do with whether this fits good or not. But this looks a little bit better, right? Before it was real tight here, and then we just saw a clear pattern of where it got bigger and bigger. Okay, it doesn't look like there's quite as much of that going on now. So that transformation does seem to have fixed a lot of that megaphone shape, that non-constant error variance. Because just looking at this, right, the spread here, and looking at back what it used to look like, right, there's a clear pattern here, whereas it starts to look a little bit more like a random scattering here, right? Maybe there's a little bit, right, but not nearly as much. Okay. Okay, here is another example. We fit our simple linear regression model. Now, one thing is, hopefully you can notice, even just from here, that it doesn't look like a simple linear regression model is appropriate for this data. Notice how all these points we kind of over predicted, all of these points we under predicted, and then back to here, all these points we over predicted. That's because this is a straight line, but this we've got a curve, right? Meaning we need to model, we don't want a simple linear regression model, we want a slightly more complicated model. Now, if you do something like this, where basically you have the wrong regression function, right? Instead of a simple linear regression, we clearly need to account for this curvature. But one nice thing about this residual plot is look at this residual plot. Okay, not only can we clearly see that this is not good at all, right? All of these residuals are low, all of these residuals are high, all of these residuals are low, right? Or negative, positive, okay? So clearly this is not a random scattering of points. This is a pattern, right? Which we don't want to see, okay? But this is less indicating that the observations are correlated than indicating that the response or that the residual function is inadequate. One way to tell that is because we've got this nice curve here. And not only does that indicate that there's a problem, it indicates the shape of this actually indicates what's wrong, okay? It actually indicates that there's curvature in the true regression function that's not accounted for by the model, okay? So this residual plot alone is kind of indicating to you that we need a squared term in our model, okay? Much more common when you have correlated observations. Much more common, you might just kind of see like a more like a straight line. Just like right, we just kind of have high residuals and then they just kind of keep going lower and lower, or vice versa. That might be a more common thing to see correlated observations, okay? So looking at this, I mean, either way, you can immediately tell that the assumptions are violated, right? This is clearly not a random scattering of points. But in this case, it's not really because the observations are correlated, but rather because the regression function is misspecified. Okay, it's not a straight line, or this data does not appear to follow a straight line, but more of a curved line. Okay, curved line. And so you can see that's what he's trying to do. And so now he's trying to add the squared term, and look what happens, okay? So now we can clearly see adding the squared term, that x squared, what allows us to not fit a straight line but a curved line. Okay, so if you fit the model y is equal to beta naught plus beta 1x plus beta 2x squared, then you can actually still graph that because you have 1x, and what that will allow the line to do is curve to account for this curvature. So you can see this is much better than that simply straight line. And looking at this, right before this graph looked like this, and now it looks like a random scattering of points, right? We've got points below the line, points above the line, in all places, and kind of how far they are away from the line is relatively similar for the different x values. Okay, so this looks great. One thing that this is actually pointing out is, unfortunately, sometimes when you correct one violation of the assumptions, you can actually make another assumption worse. For example, for this data set, this was the QQ plot, the normality plot for the residuals for the simple linear regression. Okay, and it doesn't look amazing, but it doesn't look that bad. Okay, now this is the residual plot, or sorry, not the residual plot, the QQ plot for the quadratic regression function that we fit, right? When we added the squared term, and notice it actually made this much worse. okay? So if we just looked at this, right, everything is perfect. Unfortunately, when we made this correction, we actually impacted the normality of the residuals in this case, right? These are clearly just absolutely horrible. And so sometimes you might just be left with the choice of which assumption, right, is worse. But one thing that you could go on to try to do is you could try to transform. Sometimes when you have non-normality, kind of like correcting the constant error variance, you can think about transforming one of the response variable, but also sometimes you can think about transforming the predictor variable, okay? Um, Sometimes this can be easy to fix, sometimes not, okay? So you could try maybe transformations to try to get this um, to look a little better. Sometimes it might work, sometimes it might not, okay? But clearly the normality assumption at least is violated. And why that could matter is when we think about doing like confidence intervals for the regression parameters, like confidence interval for the slope parameter or whatever, those confidence intervals rely on the fact that the data is normally distributed. So when the residuals are not normally distributed, it impacts those confidence intervals into making them not necessarily valid, okay? So things like that. Okay, so let's go ahead and do a problem, okay? So homework 6, I sent this to you with the solutions. So we're going to do one, and really I'm not sure whether we're going to stop there or not. We'll see. Okay, so we have data for the lifetime of a certain type of wire, and we also have the thickness of the coating of the wire and the temperature of the wire's surroundings. And we're trying to create a linear model for the lifetime of the wire based upon the thickness of its coating and the surrounding temperature. Okay, so we're trying to model lifetime of the wire, implying that that's y, that is the response variable. That if that's what we're trying to model, that must be the response variable. And based upon those must be the x variables, the predictor variables. Okay, so we're trying to use thickness of the wire's coating and surrounding temperature to model how long is this wire going to last. Okay, so first thing, create a scatter plot of lifetime against thickness. Does there appear to be a relationship? Okay, well, first we have to get this data into R, right? So wire, let's put that on our desktop. Wire's there, and we need that line of code, okay? Of course, if you've memorized how to do this, you don't necessarily have to copy and paste each time, but personally, I just think it's easier just to copy and paste this. And what are we doing? Okay, I'll just call it. I'll call it wire. Okay, so we can see we have our data in. We have 30 observations. We've measured lifetime, coating, thickness, and temperature. And notice what I called my data set does not conflict with one of the column labels. If it did, I'd probably need to, that would be a bad choice because that would prevent me from attaching it, right? And remember, attaching it is what allows us to use these labels directly instead of having to use like the bracket trick, okay? So I can attach my wire data set so that I can use my column labels. And first thing it wanted a scatter plot of lifetime against coating, I think. So plot coat comma life, I think, x y. Yep, okay, x plot x comma y. So does it ask us any questions? Does there appear to be a relationship? Okay, I think clearly we can see that there's a relationship. Just very first glance, we can see as code is going up, a lifetime is going up. So the thicker the coating on the wire, the longer the wire is going to last. Okay, kind of common sense. Well, it makes sense. Okay. Um, if you look at it a little closer, maybe there's a little bit of a curve going on here, right? Maybe. Just trying to fit a straight line. It looks like maybe there's a little bit of a curve here. But either way, there does clearly appear to be a relationship between the coating thickness and the lifetime of the wire. Okay. I think B asks us to do the same thing, but with the second variable, the temperature, ambient temperature. Now looking at this, I don't see a relationship. Okay, whether linear, quadratic, right, cubic, some other strange function, exponential, right? I see no pattern here between coating and temperature. To me, this looks like a random scattering of points, right, at these different coating values. Sorry. It helps if you put the right variables, okay? Temperature. Okay, so right, we had temperature, which is not the y, and we had coat, which is not what we wanted. So that was, so now we can see we have temperature and lifetime. Make sure you have the right variables. Again, though, this looks like a pretty random scattering of points. Just pick a random temperature value. It looks like lifetime is just scattered, right? I don't see fitting a line or a curve or right, a cubic or anything really. Okay, so based on this, I don't see temperature affecting the lifetime of the coating. Okay. Um, okay, so based on this, I would say does not appear visually that temperature is impacting lifetime. Okay. All right. So number C, we must choose between the following 5 models. Okay, and I mentioned here it's common um, when you're trying to model data. If you say obviously we have two different predictor variables, x1 and x2, and we have our response variable, right? That's what our data set contains, is those 3 variables. So it is more common to potentially fit a larger model and see if we can kick out terms. Okay, that's a common approach. So in this case, for instance, um, well, in this case, we're only given the choice between these 5. Okay, so if that's the case, it makes the most sense to fit this big model and see if we can kick out any of these terms in order to arrive at one of these smaller models. Okay. Another approach that you could do is try to fit one of the simpler models and see how well it fits. Okay, you can try to compare how well it fits, also look at some of the assumptions. Okay, but that's what we're going to do. We're going to fit this model, the bigger model. So what does this include? This includes, of course, the response, and it includes, so x1 is thickness, so it includes thickness, it includes temperature, and it includes squared thickness. Okay? Right, if you recall right from our first scatter plot, it looked like it looked like there could have been a little bit of a curve. So we're going to try to fit this model. Okay, well, let's go to our code. So reg model, we have lifetime, Oh, I'll have to show you something. We had coding. We also had temperature. I'll call it coat.sq, squared coding. Okay, there is one additional step that we have to do, which is sad that we can't simply put coding squared here, right? We want coding squared to be one of the predictor variables. Unfortunately, you can't just put coat squared. You actually have to put something like this, and you have to predefine it to be coat SQ. Again, whatever you define this to be can be anything, but to make it coat squared, okay? Because ideally, it makes the most sense to simply put that right here, but unfortunately, it doesn't like it. If you try that, it's going to, it actually gives you something, but it basically just ignores this, I think. So it's actually bad, it's just really bad design, unfortunately, in R. So an additional step here, if we want to include a term like this, and I think the same goes if we want, actually, I don't know. I'm not sure whether you have to do things like log, and exponential. That might work here. I'm not positive. Or you may have to predefine it. But this, I'm almost positive you have to predefine coding squared. So, and just to see, right, these should be the squared values of coding, right? So just kind of looking at this third one, right, this should be almost exactly 4, just to kind of see, right? Okay, so these are the squared values of our coding variable. And now, so we have the regression model of regressing y, our lifetime, on coding, temperature, and squared coding, which was the biggest model. Okay, and this is our model. But of course, this has absolutely nothing to do with whether this is a good model or not. Okay, so the first thing we might do is, as I said, we fit this bigger model, and we might want to see, are these terms important in the model, right? And summary reg.model, we get our p-values in this last column. Remember, right, these p-values test whether beta 1 is equal to 0, beta 2 is equal to 0, beta 3 is equal to 0, right? And if it is 0, that implies that this term is not needed, and thus we can kick it from the model. Recall, these p-values can only determine if a single predictor can be kicked from the model. You can never kick more than one thing, okay? So if there were, say, 2 things here with high p-values, again, I'll say p-value greater than 0.5, and that's what it should be unless otherwise specified. You would have to use a partial F test to determine if those could be kicked from the model. Now, if all 3 of these had high p-values above 0.5, you would look here to determine if everything could be kicked from the model, okay? But looking, what do we have? We've got a low p-value, right? Basically 0, 0.0004, and then 0.38, right? So assume our significance level is 0.05. Based on these, it appears that we can kick temperature from the model. Recall, that's the second scatter plot that we did, and it looked like, for the most part, a random scattering of points, to where it didn't look like as temperature changed, lifetime changed, right? And so that's kind of confirmed here, that it looks like we can kick temperature from the model, okay? And so that's what we're going to go ahead and do. We're going to kick this from the model, right? Because this is significant, right? The beta 1 does not appear to be 0, right? We're rejecting that null hypothesis, and that this p-value is also less than 0.05, so we're rejecting that beta 3 is equal to 0. Only beta 2 appears that it could be 0. Thus, we can kick temperature from the model and fit the model with just coating thickness and squared coating thickness. Okay, so let's do that. So I'll hit up a couple times to go back to this line. I would delete temperature, and I'll call this something different, okay, just so I can keep my first regression model and refer to it if I need to. Okay, so now I'm modeling lifetime versus coating thickness and squared coating thickness, still just separated by the plus sign. And I'll just jump right to the summary. Okay, each term appears significant. Okay, all right. Another thing though, how much did we lose? Okay, I'm still going to check assumptions, but how much did we maybe lose by kicking that term out, right? It said we could kick it out, but just roughly speaking, how much did we lose? Okay, one way to kind of look at that is R squared, right? Coefficient of determination. The model, which includes coating, temperature, and squared coating, accounts for approximately 91% of the variability in the lifetime of the wire, right? So that's a very nice number. Okay. Now, when I go down to my next model, my second model where I kicked temperature out, the only possible thing for this to be is the same or smaller, okay? When you have fewer terms, fewer predictors in the model, you can never, it's impossible for R squared to increase in a model that has fewer terms, okay? But what you want to look for is how much did it decrease? Okay, because if it didn't decrease by much, that's kind of further evidence that temperature was not impactful in predicting your response. Okay, so 91. Now in the model, which does not include temperature, it accounts for almost 91. So you see, we lost almost nothing, right? As far as variability in the response, these two alone still account for just under 91% of the variability in lifetime. Okay, so that's further evidence that temperature just was a useless variable in this case in predicting the lifetime of a wire. So I mean, that's good information to know, is that variable really does not seem useful. Okay, and I think we can actually graph this now because we still only have one variable here, one predictor variable here. It's just we have a regular and a squared term. Okay, so we could actually, I think, look at a graph of that. Okay, that'll be this AB line. Okay, but we need to get our we need to get coding on the x-axis again. Okay, so plot coat comma lifetime. Okay, code comma lifetime. And now AB line, making sure you put, if you changed the label to reg.model2, make sure you change the label. I didn't like that. Okay. Okay. I guess it doesn't like that. Let's see. I think we can do it a different way because I want to just show you. I'll do this. Y is equal to function of x. Curly bracket. What's our intercept? Intercept plus beta 1 times x minus, well, let me get rid of my minus, or plus beta 2 times x squared, right? This is our fitted regression equation, right? This is how we predict, this is how we get that regression line, right? In this case, it's a curve, right? Because we have a square term, but we have beta naught. In this case, these are all hats, right? Estimates, beta naught hat plus beta 1 hat times x plus happens to be a negative beta 2 hat times x squared. Okay, that is our regression equation. Okay, I want to go back to my scatter plot of x versus y, coding versus lifetime. And now I think if I put curve y, add is equal to t, add is equal to true. Let's see if that works. And there you go, okay? Of course, if I wanted it red, I could do color is equal to red. Okay, maybe I'll do that just to get a nice looking plot here. Color is equal to red. Line width is equal to 2, makes the line a little thicker. And there you go, okay? So you can see this does a lot better than fitting a straight line. Okay, right? A straight line would not be able to capture this curvature that we have. Okay, so now, right, our regression equation still only includes one predictor variable, but we have both its linear and squared term, such that, for example, if I wanted to predict the lifetime of a wire that had 2.5 millimeters of coding, it's the same as simple linear regression, right? You go up to the line, and this must be my prediction, okay? Right about 19, a little less than 19 or so, or 18 and a half, somewhere in there. And all you do to get that is you plug in 2.5 into this, right? So you have, I won't be lazy, okay. So if that's what I wanted to do, here, I'm gonna do it like this. This is annoying. Actually, I think I can do it like this. Can I? I'm not sure. We're about to find out. Okay, I can. Okay. I said y is equal to a function of x, and I basically defined this to be my regression equation. Okay, so maybe I should call this like y hat actually, right? Because this gives me my y hats, my fitted values. Okay, so that might actually be even something to potentially do. Just to be clear, right, this is our fitted regression equation. And so now, if I want the prediction of my regression model for 2.5, all I have to do is put y dot hat, in this case, whatever I called it, put 2.5, and it spits out the number. And again, right, we said it should have been about 19, and right, that's exactly what it is, 18.86, etc. Okay? So that's a way that you could also get those fitted values easily. Okay. Now, again, if I have two variables, such as if I had to include that temperature variable also, to where I had life and then coding and temperature, that's when I can't have a nice graph like this anymore. Okay. It's only if you have a single predictor variable and you might have nonlinear terms such as a squared or cubic term or something, you could still look at it in a nice graph like this, but never if you have more than the one predictor variable, really. Okay, so everything here is indicating that this is a good model, right? This is a better model than this because this term appeared non-significant, and not only does this indicate that we can kick it out, we also gained evidence that when we did kick it out, we lost almost no prediction ability, right? No variability in y was captured by that temperature variable. Okay, so that, along with this, in this case, we can look at this nice graph as seeing how well it does kind of fit the data, is indicating that this is a good model. Okay, we capture a good, nice proportion of the variability. The terms are significant, it fits the data well, but what we still have not captured or verified are the assumptions on the error term, okay? They could be horribly violated and we have no idea, right? So let's go ahead and check them. Okay, so I think all we have to do is put plot. Now normally we do plot x comma y, right? But there's something else that this plot function can do, is if we put plot and then put whatever we called our regression model. So in this case, right, I want to verify this model because this is kind of clearly a lot better than the first one. I want to make sure that these assumptions or that the assumptions are satisfied. Okay, so when you do this, you see it says waiting for page to change, and you have this. This does not mean that R is loading or freezing, okay? So if you do this once and you don't pay attention, you'll probably be confused. What you have to do is it's got multiple graphs that it's about to show you, and you simply have to click each time you want to change graphs. So the first time you have to click, and let's see, maybe we have to click the graph. It's been a while. Okay, you have to click the graph. Okay, so that's another reason it could confuse you. If you start clicking over here, you're going to have no idea what's happening. You actually have to click the graph. So if you haven't done that before, it'd be very easy to just think that R is frozen on you. So the first graph that it's going to give you is the residual plot. Recall, this is where we can check all of the assumptions except whether the residuals or whether the error terms are normally distributed. Okay, so this is one of the things that we look for, and it's also going to give you in this plot function, it's also going to give you this nice red line. Okay, and so that's also a nice tool because perfectly in the perfect case, we want this line to be horizontal at 0. Okay, right? Because the expected value of these error terms we want to be 0. Okay, but what we can see it strays a little bit, but overall this looks great. Okay, but you cannot simply look at that red line alone. Okay, because that if you only look at this red line, it's possible for the variance to be changing and you not to be able to notice that. Okay, so we also want to look at the spread. We want a nice random scattering of points. So what we have, right, we've got some spread. Looks like there's really no data points here. There's not very much data here, so it's kind of hard to tell. If we kind of ignore those 3 points for now, it almost looks like we kind of have that megaphone shape going on a little bit. Okay, but we also have these 3 points here to where the variability here is about the same as the variability here. Okay, so I would say that that's not a huge issue in this case. If these 3 points weren't here and it kind of started here, it would kind of look a little stronger evidence of that. But I would say because, right, we still do have a nice spread here. It just goes, it's like a little bit of spread, gets a little bit more narrow, and then flares out a little bit more. Maybe not perfect, right? We'd like a little more points here, but not terrible either, okay? Again, if it just started here and there was no kind of extra variability here, that would be a little more indication that maybe the variance is non-constant, okay? But this, not perfect, but as far as the non-constant error variance, but probably not enough that I would that would warrant trying to do transformations or other procedures to try to, fix it. I don't think it's probably worth that. It's not that bad. Okay, as far as there being some pattern, right? As far as being like a pattern, again, most of the other stuff you can just kind of look at the red line, but I think a due diligence, you should kind of look at the random scattering. It looks pretty random, okay? There's not a bunch of points below the line and then above the line. There's no kind of pattern, okay? So everything looks pretty good there. Again, the only assumption, potentially a little bit suspect maybe, and it could only be because there's only a couple points here too, right? Is the variability here a little bit smaller than here? It does look like it, but it's a little more here also. So it's quite possible just because there's only a couple data points here. Who knows? Okay, but overall, I'd be happy with that graph. Now, when we're ready to switch, you just click the graph again. And now this is the QQ plot. Okay, so this is the one verifying the normality of the error terms, right? Technically, it uses the residuals, but this is what helps us gain evidence of whether the error terms are normally distributed. And this looks great. Okay, this just looks really nice. Okay. Okay. Again, these are all above the line, which isn't perfect, but they're not far above the line either. So overall, I would say that's great. Okay, so based on those two graphs, it looks like the assumptions of our model are satisfied. Okay, now there's a couple more graphs that I'm not worried about. You can just ignore them, but technically in order to get back to using R again, you just have to click through them. Okay, so two more graphs, and once you've clicked through them, you can go back and you can use R again. So So right now, I would determine that this model 3 is the model that we need to use, right? We need thickness and squared thickness in our model. We do not need temperature in the model, and it does not appear that we can kick out thickness or squared thickness, right? So model 3 appears to be the best. It captures a large amount of the variability, which is nice. The p-values are small, indicating that they're significant. And the assumption, it fit that we had that nice graph, that nice curved scatter plot, and the regression line went right through the data nicely. And our residual plot and our QQ plot indicated that the four assumptions that we have on the error term appeared satisfied. Okay, so this clearly appears to be the best model among the five. Now, one thing to notice, right, we started here. We determined that x2 does not need to be in the model. Okay, so that kind of automatically eliminates this. And then so we tried to fit this model, and we determined that this model fits really well. Okay, now one thing that you could be thinking is can I fit an even simpler model? Okay, right? So the squared coding does still appear significant, but maybe I'd really like a nice interpretable model, right? You can't get any more interpretable than a simple linear regression model, right? Where you just have y and x, okay? So, and maybe one thing that maybe you didn't even start by fitting the thicker or the bigger model. Let's just say, for instance, let's say you started here, right? Okay, we're going to go ahead and do that. Okay, maybe it didn't even cross your mind. Maybe you didn't look at that scatter plot at the beginning and look and see that maybe this squared term is needed. And another thing that I will say, and I'm going to go ahead, another thing that it is common to do is fit an interaction term, okay, which is would be y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2, and then of course plus epsilon, okay? And that interaction term is kind of saying, do x1 and x2 interact in some way to affect y, not just individually, but kind of their combination to affect y, okay? The main reason that I didn't include that as an option is it's probably not, I'm going to go ahead and look at it. It's probably not going to be significant. I'm positive it's not going to be significant. So I'm going to call this reg.model 3. So I'm going to look at coding plus temperature plus coding times temperature. Okay, this would be the interaction. So summary reg.model 3. Okay, so right, we have y is equal to beta naught plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x1 times x2. And now notice we have a large p-value for this and a large p-value for this. This is indicating that neither one of these appears significant. But as I have said before, but this is, right? So this p-value only says, can we kick everything out of the model? And of course, if this is significant, then this surely will be significant. But you could look here and see, okay, we can't kick everything out of the model. But to determine if you can kick both of these out of the model, really what you should be doing is an overall f-test. It's not a good idea necessarily to just kick this out of the model, say, kick this out of the model, fit the model with just these two, and then if this is still big, kick this out of the model, okay? The best thing that you should be doing is an overall f-test to determine if you can kick both of these out of the model. And as I've said, I told you that's what you should be doing, but for time's sake, we're not going to necessarily go over exactly how to do that, okay? So what I'm going to do here is we're kind of redo the problem. And as I've said, let's pretend that ignore this is even an option. Let's pretend we started with this, right? We've got our two predictor variables, right? Coding, thickness, and temperature. And so the easiest thing to do would kind of be to fit this, right? This is with those two predictor variables in the model, this is the simplest model we can do, right? Beta naught plus beta 1 times x1 plus beta 2 times x2, okay? That is the most simple model that contains these two predictors, okay? So maybe that's the way we approached it, is at the most basic simple level, okay? And that would be this model here. Reg.model 4, it includes the model for lifetime versus coding and temperature as my two predictors. Okay, summary reg.model 4, make sure you put the right one. We can see we have coding and temperature. And we can see here, right, use our alpha is equal to 0.05. This is a very small p-value. This is a very big p-value. This indicates that we can kick this from the model, okay? So let's go ahead and do that. And let's call it reg.model 5 now. It appears, again, based on this p-value, temperature is not needed in the model. So thus, the only thing left in the model is just coding. So let's fit that. So summary reg.model 5, we got a significant p-value. And one thing to look at, how much kind of variability in y did we lose by kicking out temperature? So the model that includes only coding captures 85%, and this captures almost 85.5%, right? So almost nothing more, right? So another indication that we really did not need temperature in the model. Okay. And so let's look at that actually. So plot x comma y. And now AB line, this is reg.model 5. Okay, and so since this is a simple linear regression model, I can just use this simple line here and not have to define that function that I did before. And so this is our model. And to be quite honest, that doesn't look too bad, right? It doesn't look as bad as I thought. I mean, yes, these are a little bit below. These are still pretty scattered a little bit, and then you know we actually have one that's above the line. So to be quite honest, that doesn't look too terrible, right? I think that curved line still hit it a little better, but that doesn't look terrible. And I'll tell you one thing, we haven't gone to interpretation yet, but this, right, you can't get any more interpretable than this, okay? Right? This is the intercept, which we'll get to, but really coating, for every 1 millimeter, we increase the coating of a wire, it lasts 2.3 more years, right? You can't get any more interpretable than that, which is great. So how much, well, and one thing that I'll look at is we also fit the model that including coating and coating temp squared. So how much more variability in Y did coating squared capture? Well, here's 85. If you recall, I think it was about 90, right? We're looking for coating and coating squared. Coating and coating squared. So it captured about 91%. So it captured about 5 to 6% more of the variability in Y by including this term, okay? And clearly we can see it's significant, and I would say that that's not a trivial amount of variability captured by adding that. So that's also kind of evidence that maybe the squared term was needed, okay? But I want to say maybe we're really valuing the interpretability of the model, okay? Yes, it looked like the squared term was needed and it did capture a little bit more variability, okay? But maybe we'd really like a simple model. But what we still haven't done is checked the assumptions, right? So let's go ahead and look at that. Reg.model 5, plotting reg.model 5. Got to click. What do we see here? This is bad, right? Despite the thing saying yes squared, the p-value for coating squared was significant, right? Go up. And that it captured about 5 to 6% more variability in Y, which is not trivial, also indicating that that squared term is needed. But if we're really just trying to go for a simple linear regression model, right, then maybe we could overlook that. But we still have to have these assumptions satisfied. And what do we see here? This is bad, right? This is nowhere close to a nice straight line at 0. So if this is the model that I was trying to fit, even if I never fit the model with that squared term, I can immediately see this is not a good model, okay? Because of this, right? This is clearly not a red line at 0, and what's clearly happening is we have a curve. And as I've said before, sometimes that can indicate the most common thing that's going to indicate is that the regression function is misspecified. And if there's a curve like this, it's usually going to mean that there's a quadratic component needed in the model. Or sometimes it could be some other transformation is needed, but that is the most common thing. Okay, so even if you didn't start from that bigger model, right? Maybe it didn't even cross your mind to put that squared term. You can still, by checking the assumptions, catch yourself from thinking that this simple linear regression model is the best, okay? Or even really kind of getting away with it, right? This indicates that it's most likely, right, if say we haven't fit the bigger model, it's most likely indicating to us that we need a squared component here. Okay, now without fitting it, we can't just immediately say, oh, it's going to fix everything, right? But that is the most common thing that's indicating. But what it's definitely indicating is that this is not an appropriate model, that the assumptions are not satisfied for this model of just Y versus X. Now, if we go to the residuals, the QQ plot of the residuals, these are perfectly fine. Okay, that's perfectly fine, but that doesn't really matter because we already saw from the first graph that the simple Y versus X model, simple linear regression model, is not appropriate. Okay, so great interpretation, but we saw, I think it was reg.model 2. Yep, We saw that this model, the squared term is needed, right? So that might be, after looking at that graph, that might be the next thing that we tried if we hadn't already, is adding the squared component. We can see that yes, based on this p-value, it does look like the squared component is needed. We also saw that it improved the proportion of variability explained by the model of y, explained by the model, r squared, increased from 85, right, to about 91. So definitely a noticeable increase in r squared. And then, but beyond that, plotting, right, before we had this TP, right, and then now we go to this, right? Clearly, this is way better than what we just had a second ago, which is basically a pyramid, right? So we can see that this also fixed the assumptions. Okay, and so based on everything, this is by far clearly the best model. Everything is significant. It explains almost the most variability, right? Including temperature, increase this just the tiniest of bits, and the assumptions for this are all satisfied. And so this looks like a really good model. And of course, with only one x, we were also able to graph it. Right, using this, y hat is equal to function, parentheses x, curly bracket, put exactly what the regression function looks like, right? And then you can plot x comma y and then curve it and add it, okay? So everything led to the conclusion that Model 3 is the best model, okay? What are the least squares estimates of the parameters of this chosen model, right? This should be the easiest question possible, right? Those are just your beta hats. So the least squares estimates. Make sure we're going back to the right model. We've fit a few different ones, but we know it's coding and coding squared, x1 squared. The least squares estimates, beta naught hat is equal to this, beta 1 hat is equal to this, beta 2 hat is equal to that. Okay, pretty simple. If the parameter estimates have a nice interpretation, provide it. If they do not, explain why. Okay, so let's look. Intercept. Is the intercept interpretable in this example? Well, if we have a coding of 0, right, plug in. So of course our model looks like this y hat here, which was somewhere. I'll go ahead and put it in the other page. Right, so this is our regression equation. And so plugging in 0 for x for coding, right, just eliminates those. And so we have that we expect the lifetime of a wire that has basically no coding, right? No coding, 0 millimeter coding, no coding, to be 9.47 the intercept years. So that actually has a very nice interpretation. I'm guessing it was years, in years, okay? Because we could easily produce a wire with no coding, right? So we saw a lot of examples where the intercept was useless. This actually makes sense, okay? So if there is no coding on the wire, then it's going to last about 10 years. So that actually makes a lot of sense. What about beta naught and beta 1? Sorry, beta 1 and beta 2. Now in simple linear regression, right, this has a very nice interpretation. When we increase coding by 1 millimeter, lifetime increases by 5.5 years. Okay, that's very nice interpretation. We do not have that in this. Okay, think about trying to increase x by 1 now. If we increase x by 1, well, this is x squared. So if we increase this x by 1, we're increasing this x by 1. And so now, because there's this squared component, it matters where x is as to how much changing x matters, right? So when we change x from 0 to 1, right, we're adding this and we're subtracting this. But if we change x from 4 to 5, we're still adding this to x, but now we go from minus 16 of these to minus 25 of these, right? So because there's this squared term, it completely renders the interpretation of beta 1 and beta 2 uninterpretable, okay? So even in almost the simplest case, right, just slightly more complicated than simple linear regression, we've kind of killed the interpretation of these parameters, okay? So not ideal. Beta 1 hat and beta 2 hat, not interpretable. But we clearly saw that this is certainly the best model. We unfortunately do sacrifice a little bit of interpretability, but it's clearly better than if we kicked the squared term out of the model. Okay. All right. I want to save the last 2 lectures for review, so we are going to skip the 2x2 factorial design. Okay, so I plan on my last 2 lectures being review. All right.